Hi, I am Lorenzo Ciardo from the University of Oxford, and I will talk about approximate graph coloring and the hollow shadow, a joint work with standard Zivny. Let me first define the problem. In the search version, we are given two integers c less than or equal to d, and the problem is, given a c colorable graph G, find an explicit d coloring of it. In the decision version, again, we have c less than or equal to d, and the goal is to distinguish whether a given graph is c colorable or it's not even d colorable. By coloring, I mean assigning colors to the vertices of the graph in a way that two adjacent vertices get distinct colors. The results I'm going to talk about hold equally for the search and the decision versions, so I'm not going to distinguish between them further. Garay and Johnson in 1976 conjectured that this problem is NP-hard for any constant C and D at least 3. So if C is equal to 2, then the problem reduces to checking whether the graph is bipartite, which is tractable. Let's look at the progress on the solution of this conjecture. So if C is equal to D, what we get is C coloring, which is NP-complete. It's one of CARP's list of NP-complete problems. If C is equal, for example, to 3 and D equal to 4, this is also hard, as shown 20 years later by Khanna, Lineal, and Safra, and a different proof was given by Guruswamy and Khanna. C equal to 3, D equal to 5, also hard, shown 4 years ago by Bulling, Krokin, and Opschall. And you see that the bigger the gap between C and D is, the easier the problem potentially is, so the harder it is to show hardness. Asymptotically, the best hardness result is due to Rockne and Zivny, who proved that the problem is hard when D is C choose C halves minus 1, so roughly exponential. But already, for example, for C is equal to 3 and D equal to 6, the complexity of the problem is still not known. So there's a huge gap in our understanding. All right, so let's look at the problem in a bigger generality. So let's look at constraint satisfaction problems. We are given a template, a fixed template T, and a variable instance G. And the problem is, in the search variant, assuming that G is homomorphic to D, find an explicit homomorphism. In the decision variant, we need to distinguish whether G is homomorphic to T or not. Here, T and G are graphs, or we may want them to be hypergraphs, so the edge relation has a higher RET. We may also want that there are many different relations with arbitrary RETs. So it's customary to study CSPs over relational structures, but for the purposes of this talk, it's enough to think about graphs. So some examples of CSPs, well, if the template contains all solution sets of linear equations, so affine hyperplanes, then the CSP models a system of linear equations. Horn-SAT is also a CSP for a suitable template, as well as its variants, 1 in 3 SAT, NAE SAT. Sudoku is a CSP. The vertices of the instance are the cells in the grid, and the vertices in the template are the numbers I want to put in every cell. Graph coloring is also CSP, of course, because a graph is C colorable if and only if it is homomorphic to the clique, having C vertices. All right, and then we see that approximate graph coloring is an approximate version of a CSP. So it's an approximate CSP. And this kind of approximations of CSPs have become quite popular recently under the name of promise CSPs, especially after Barto, Bulling, Krokin, and Opschall developed an algebraic approach to their description. So how do we solve a CSP? I'd like to argue that there are exactly two methods or two philosophies to solve such a class of problems. The first one is to treat it as a system of linear equations. So every CSP can be associated with a 0-1 system of linear equations. This is not solvable in polynomial time where 0-1 most likely, so we relax it and we solve it, for example, over the integers through Gaussian elimination or a variant of it. And this gives us a relaxation. Another way is to solve it as if it was a Sudoku. So to solve a Sudoku, the kind of the standard method is to look at the first cell, look at all the numbers we can plug in it, then look at the second cell, look at all the numbers you can plug in a second cell, and so on, until we find some contradiction. And when we find a contradiction, we can remove possible assignments. And of course, if I'm a human being or a computer, I have a limited amount of computational power, so I cannot look at contradictions coming from analyzing all the cells simultaneously. I need to restrict on, let's say, k cells at a time. But this gives us an algorithm that is called k consistency, local consistency, and there exist more refined versions of it that make use of linear programming, so the Shirley-Adams hierarchy, or semi-definite programming, the sum of squares Lasserre hierarchy. All right, and well, it was shown by Barton and Kojic that if I have a tractable CSP, and this is not solvable by local consistency, then it can somehow simulate linear equations. And through the dichotomy theorem for CSPs proved independently by Bulatov and Zhuk, this, roughly speaking, means that a CSP is tractable if and only if it is some combination of linear equations plus Sudoku. Okay, so on its own, the integer Gaussian elimination is not able to solve all CSPs, and the same thing is true for local consistency. So these two methods on their own are not powerful enough to solve all tractable CSPs. So efforts have been put to try and find a unique algorithm mixing these two philosophies with the aim of finding a universal algorithm solving all tractable CSPs. And one step in this direction is the following hybrid algorithm described by Brakensick and Goswami 3 years ago. Basic linear programming plus affine integer programming, BLP plus AIP. So I'm going to call it in this talk as the algorithm. So this algorithm here has some nice properties. So first, it solves all Boolean tractable CSPs or Schaeffer dichotomy. It naturally comes as a hierarchy, the same as Shirley-Adams solve or sum of squares. And this hierarchy is at least as strong as both the method I mentioned. So it is at least as strong as integer Gaussian elimination and local consistency. It is sound in a limit, in a sense that if I take some instance having k vertices, then the kth level of the algorithm is always able to classify it correctly. This is actually already true for local consistency. And it is conjectural, it may solve all tractable CSPs, exactly because it combines these two philosophies, and a CSP is tractable if and only if it is a combination of these two templates. All right, so let's go back for a moment to approximate graph coloring. So we've seen that approximate graph coloring is not a CSP, it's an approximate CSP, but we can apply the same kind of algorithms also to it, also to approximate or promise CSPs. So it is known that constantly many levels of the sum of squares SDP hierarchy do not solve approximate graph coloring. And of course, this result also holds for local consistency and Shirley-Adams, which are weaker. And this comes from the proof of the 2-to-2 conjecture by Dinur, Kindler, Mincer, and Safra 5 years ago. Even sublinear levels of local consistency actually do not solve the problem, as shown by Atzeres and Dalmau. And recently, we showed that also the other method, so integer Gaussian elimination, is not strong enough to solve the problem. Okay, so the result I want to talk about is the following. So approximate graph coloring is also not solved by a combination of linear equations and local consistency. In other words, it's not solved by the kth level of the algorithm that I presented you before. So it turns out that a key step in order to prove this theorem is simply to come up with the right formulation of the objective. Once that will be done, then the proof will follow kind of naturally. So the first way of formulating the objective is the following. So we want to show that some problem is not solved by some algorithm. So all we need to do is to present a Falling instance. So in this case, a graph G such that the algorithm thinks that G is C-colorable, but actually G is not even D-colorable. So the first refinement of this formulation of the objective comes from tensor theory. So recently we developed a framework that we call the tensorization that allows us to view hierarchy of relaxations in a geometric way. More precisely, for suppose that H is a hierarchy of relaxations and let T be a template graph. Then for any K, we can produce a space of k-dimensional cubical tensors. So a space of tensors that are cubical, so all the modes have the same length. So in 2 dimensions, they will be a square matrix. In 3 dimensions, they will be a cube, and so on. And this space have the following property. So given an instance graph G, the kth level of the hierarchy accepts G as an instance of the CSP. So it thinks that G is T-colorable in a way. If and only if there exists an assignment, so a map Xi taking tuples of vertices of the instance and returning tensors in the space. And this assignment needs to be consistent in some geometric way. But besides technicalities, this allows us to see a hierarchy of relaxations in an entirely geometric way. So rather than looking at the behavior of the relaxations on specific instances, we can simply study the geometry of this tensor space. So in our case, so if H is the hierarchy of algorithms that we are looking at, this is a space of k-dimensional integer tensors of width C. So the width is the length of the side of any hypercube of any tensor in this space, and C is the number of colors. And an assignment is consistent if whenever I have a tuple x1 through xk of vertices, then the tensor I associate with it is such that all the non-zero entries lie in some subspace that is associated with the tuple. So a geometric notion of consistency in a way. Okay, then we can see an example of this. So we want to look at assignments of this kind. So we take a tuple of vertices like x1, 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 and then we associate to it a tensor where all the non-zero entries lie in some hyperplane. Okay, so this gives us the first, or like the second version of our objective. So rather than finding a full instance, we now seek a consistent assignment of tensors to tuples of vertices. Okay, so the second refinement of the formulation of the objective comes from a notion that we called crystals. So in order to produce this assignment tensors to tuples, we will do the following. So we will pick a single high dimensional tensor that will have some properties and we call a crystal. And then given a tuple of vertices, we will interpret it as a list of coordinates that will identify a low dimensional subspace of the space where the crystal live. And then the tensor that we associate with the tuple of vertices is going to be the projection of the crystal onto this subspace. Okay, so what is a crystal? Well, we define a crystal to be an integer tensor, such that if I consider the projections of this tensor on spaces of dimension exactly k, so k-dimensional projections, I obtain all equal tensors. Right? So all the k-dimensional projections are equal up to reflection, where a reflection is a higher dimensional analog of the transpose operation. And we call the shadow of the crystal this unique tensor that equals all these projections. So let's see some example of this. So now we'll try to represent tensors graphically. So numbers will correspond to colors. Let's say that the shadow is 2-dimensional. So it's a 2-dimensional tensor, just a matrix. In this case, the matrix 0, 0, 1, 1, 0, minus 1, 0, 0, 0. Okay, then a 3D crystal would be a cube, such that if I project it onto the three possible planes, I always obtain the shadow. Here, projecting just means choosing a direction and summing all the entries of the tensor in that direction. Okay, so it's a bit less easy to see, but this is an example of a 4D crystal. So however I choose a subspace of dimension 2, or the 4-dimensional vector space, so I have 4, choose 2, so 6 possibilities, I always obtain the shadow if I project the tensor on it. Okay, so as I said, this crystal can be used to build an assignment tensors to tuples. So a q-dimensional crystal C, or width C, guarantees, so it's a certificate that the linear equations part of the algorithm accepts G as an instance of C coloring, provided that G has q vertices. Remember though that our algorithm also has a consistency part. So it is linear equations plus consistency. And the consistency is essentially telling us that some assignments are forbidden. So remember in the Sudoku, some assignments generate a contradiction. And how to see it in our tensor? Well, we say that a tensor is hollow if entries having repeated coordinates are 0, or in other words, the only entries that are allowed to be non-zero are those having all distinct coordinates. Okay, so it turns out that if we have a crystal C and the shadow of C is a hollow tensor, then this is enough to guarantee that consistency is enforced, and then that the algorithm, the K level of the algorithm, accepts G. We can then go back to the formulation of the objective and finally have the third and last version of the objective, that is, find a crystal with a hollow shadow. Okay, so now we only need to prove this, and we see that now the proof shall be completely geometric or multilinear algebraic. We don't have to think about the technicalities of the algorithm anymore. Okay, the existence of crystals. So, do crystals exist in nature? We saw some examples, but do crystals exist in any dimension and any width? Because this is what we need to rule out solvability of approximate graph coloring. We can actually approach this question in a bit more generality. So suppose that we have a set of shadows. When is this set of shadows actually the set of projections of a higher dimensional tensor? So when is a system of shadows realizable? So let's say that the shadows have dimension 1, so they're just vectors, a column vector in orange and a row vector in blue. So we want to understand whether or when there exists a matrix such that if I project this matrix horizontally, so if I sum up all the rows, I obtain the blue vector. And if I project it vertically, so if I sum up all the columns, I obtain the orange vector. So if this is the case, then you see that the sum of the entries of the matrix is equal to both the sum of the entries of the orange vector and the sum of the entries of the blue vector, which means that these two numbers need to coincide. And it turns out that this condition is also sufficient. So if the sum of the entries of the orange and of the blue vector are the same, then it's not hard to find a method to build a matrix satisfying the property. Okay, so let's look at the problem in a higher dimension. So now we have two-dimensional shadows and we want to build a three-dimensional tensor. We can look at one slice at a time, for example, this slice here, and then we look at the corresponding slices of the yellow and blue shadows, and then we reduce to the problem of before. And then we consider other slices and we do the same, but then we also have to take care that the third shadow is also satisfied. So in a way, we have more constraints. So we show that whenever we have a system of shadows, this is realizable. So it is actually the set of projections of a higher dimensional tensor, if and only if some geometric condition holds. And besides technicalities, this geometric condition is the higher dimensional analog of the fact that the sum of the entries in the blue and in the yellow and in the orange vector need to coincide. Okay, so actually the proof that we have for this is constructive. So whenever we have a system of shadows satisfying this geometric requirement, then we are able to produce, to actually build a tensor realizing these projections. And this also tells us that, well, we may consider a system of shadows such that every member is the same tensor. And then we have to check that this satisfies this geometric condition. And once we do it, then we know for free from this theorem that this system is realizable. So there exists a tensor such that if I project it, I obtain the same thing. In other words, this tells us that crystals do exist in any dimension and width. And as I said before, this is enough to show that linear equations do not solve approximate graph coloring. And actually, we can take any instance with a big enough chromatic number to be a full instance. So for example, we can be lazy and take clicks. All right, so this is not quite what we want because we want to build crystals with hollow shadows. Let's first look at this crystallization process. So the shadow of a crystal is itself a crystal. So using this and the system of shadows theorem that I showed you before, if I have a crystal, I can find a higher dimensional crystal having the first crystal as its shadow. So the system of shadows theorem gives us a recursive method of crystallizing, so creating higher and higher dimensional crystals. So this also means that the question above, so whether crystals with hollow shadows exist in any dimension and width, is actually the same as saying, do hollow crystals exist in any dimension and width? Because when we find a hollow crystal, then we can build a higher dimensional crystal having it as its shadow. Okay, so here is a method to mine hollow crystals. So we start with a crystal, for example, this one. We know that they exist in any dimension and width. Notice that this crystal here is not hollow. For example, this entry here, the 111 entry is non-zero. Then we pad it with many layers of zeros. So we want to make some space. And then the idea now is to try to get rid of the bad entries, like this entry here, by spreading them away. And we do so by summing a perturbation tensor that should be able to modify locally the structure of this crystal in order to avoid bad entries. So this perturbation tensor needs to also be a crystal because we want to preserve the fact that we have a crystal. Also, we would like not to change the shadow, which means that this perturbation tensor, this perturbation crystal, needs to have identically zero shadow. So it needs to be transparent. And moreover, we would like as many as possible of the entries of this perturbation tensor to be zero so that we don't modify, we don't mess too much the structure of the crystal we have. So this is an example of a transparent crystal, which we call a quartz. So you see that if I sum this tensor with this tensor, here I have a -1 and here I have a 1. So they're going to cancel each other out. And here I get 0 as wanted. But of course, this produces some problems, 7 more problems. So you see these entries here used to be 0, but now they are non-zero. And they are also bad, so they also contain repetitions of the entries. So it's not really clear whether this procedure helps, but it turns out that if we choose the quartzes carefully, this procedure always results in a hollow crystal. Okay, so this means that yes, hollow crystals do exist in any dimension, but notice that the width has increased. So we started with a crystal of width 3, and we ended up with a hollow crystal of width 6. All right, so this means that hollow crystals exist in any dimension and with quadratic in K. So we suspect that quadratic is not optimal. We suspect that linear is actually enough, but definitely constant does not work. So this means that we can use this hollow crystal or this crystal with a hollow shadow as a certificate that the K level of the algorithm accept our graph. So this means that the K level of the algorithm thinks that any graph is K-square colorable. This K-square is the same as the width here, so quadratic in K. And by considering again clicks, we immediately have that the K level of the algorithm does not solve approximate graph coloring, provided that C is at least K-square. Okay, so this is not quite what we want. We would like to go up to 3. So we want to rule out solvability of approximate coloring for C and D from 3 on and for any level. So we need to use a trick, and this trick is the line digraph. So the line digraph of a digraph is the digraph having for vertices the edges of the original one, and 2 edges are adjacent if they are consecutive. So the line digraph of a digraph is a digraph itself, and this provides a reduction that behaves well under the acceptance of for this algorithm, and also happens to change the chromatic number of the graph in a controlled way. So it decreases the chromatic number roughly exponentially. And I will not go into technicalities now, but it's exactly this discrepancy between exponential change of chromatic number and quadratic width of the holocrystals we built that allows us to finally extend the result up to C equal to 3. And the Fulling instances for the K level of the algorithm will be not quite clicks, but repeated applications of the line digraph reduction applied to clicks. In other words, graphs known as shift digraphs. So K applications of the line digraph reduction applied to a click. And here you see some examples. Okay, so before concluding, I want to briefly mention some follow-up work, also joined with standard Zivny, association schemes for semi-definite relaxations. So one of the goals of this work is to push the result to linear equations plus semi-definite programming. And when trying to do so, we immediately have to face a problem. The problem is that for all the acceptance results that I mentioned in this talk, they are of the kind: an n-dimensional tensor, an n-dimensional crystal provides me with a certificate that any graph on n vertices is accepted by the algorithm. So our methods essentially don't distinguish the structure of the instance. They only care about the number of vertices. On the other hand, semi-definite programming is able to distinguish the structure of the instance when applied to coloring. So the strategy for facing this problem here has been to actually make use of this fact. So we have built a way to translate the symmetries of the instance graph into symmetries of an SDP solution. And the way we operate the translation comes from algebraic graph theory, and it's through the notion of association schemes. More specifically, we can design some Fulling instances for the problem by using one particular association scheme known as Johnson association scheme, of which you see some examples here. Okay, and I think my time is finished, so thank you for the attention.